Okay, we're actually not done looking at the data. I forgot there's a few more things we need to do. So first we can use the head function here and just remind ourselves of the structure of the data. So here we can see it has 4 columns with height, weight, age, and sex. And so it's structured in this manner. Now, so we're interested in the effects of sex on individual height. One issue with that might be the age of individuals. If we include juveniles, then that could make our data noisier. So before we analyze it, we're actually going to get rid of the juveniles. Or to put that another way, maybe a nicer way, is that we're only going to use the data from adults. So here we're making a new variable called adults, and we're making that by selecting only the rows from the Howell data frame where the age field is greater than 19. So we're just going to use individuals 20 years old or older, and then we're going to select all of the columns from there. So this will be the data set that we'll be using. Okay, well, so now we'll move on to plotting the data, and there's quite a different ways that you can plot data when you have one metric variable and one categorical variable. And we'll go through a number of different ways to do this, and the goal is that hopefully by broadening your repertoire, you'll be able to choose the appropriate method for whatever situation you happen to be in. So we'll start with just a simple histogram. We're going to use ggplot here. So first we're telling ggplot what data frame we're going to use, changing that underlying theme, then plotting a histogram using the geom_histogram function. And for the aesthetics, our x value is going to be height. Then we're just changing the color and making it transparent, and then specifying the x-axis label to be height in centimeters. And so you get a plot like this. So this is okay, but it's not super helpful because there's no information about our categorical or nominal data here. If we want to include that, a common way to do this, again, when you have one metric variable and one categorical variable, is to plot the metric variable but grouped by each category, each level in your category, and you can do that with a box plot. So we can do that very easily with ggplot. So again, the first 2 lines are the same, but now we're using a geom_box plot. We're setting the aesthetics for x to equal our sex, and y is going to be height. And then here I'm just customizing what color these are used to fill in and making them slightly transparent. So here we can see box plots are quite informative. They not only show you like the mean value of a particular or of the metric data grouped by your different levels, but they also show you the distribution of the values. And so it actually can be kind of hard to figure out what these are in R, so we'll go through that here. So by default, the thick line within a box plot is the median. And so a median just means that an equal number of values fall above and below that line. So just as a recap for central tendency metrics, so the mode, the median, and the mean, we have kind of this crappy picture here, but it gets the point across. So if you have a symmetrical distribution, then the mode, the median, and the mean are all the same. But if you have an asymmetrical distribution, which we often have, these can all be quite different. And so it's important to know what each is. And so the mode represents the value that is most frequent in a list of values. So that would be the mode is the peak of a distribution. So it's the one that occurs most frequently. The median is the number in the middle of the list. So an equal number of values fall above and below the median. And then the mean is the average of all numbers. So you add them all up and then divide by the number of values that you have, and that's your mean. So these are all different measures of central tendencies that give us different information. So anyway, this solid or the thick line in a box plot is the median. Then the area outlined by the actual box itself, these borders represent the 25th and the 75th percentiles, or the first and third quartiles of the data set. So that means 50% of the values fall within this range. So we have the median and then 50% of the values fall within the box. Then we have these whiskers, and these whiskers extend to 1.5 times the interquartile range. And so 1.5 times the distance between the range within the box. That's how long these whiskers are. And then any values that fall outside that range are called outliers, and those are just drawn as points. So these are defaults that R uses, and you can change all of them to suit your needs, but most people don't worry about that. So we can also plot the original data points. So one criticism of box plots is that they present a summary of the data rather than the data itself. And so some people prefer just to plot the data. So we can do that using the geom_point function. And so here our x values are going to be our different sex categories, and y is going to be our height. And then again, we're just changing the color and making them transparent. You can see this isn't very informative because there's so much overlap between dots. And what we can do is what's called jittering. And so what jittering is adding random noise to values to decrease the overlap in points. And so of course we don't want to add random noise to the y-axis because this is the actual value that we're interested in. And so we don't want to change the data. But we do want to add noise to the x-axis, so to the width at which these are plotted, because the width doesn't mean anything, right? As long as they all fall within this male area of the curve, moving the dots around this way doesn't matter. And so that's what we want to do. We want to add random noise to the width of the area that these dots are plotted in, but not to the height in which they're plotted in. And again, this is called jittering, and it's a common function for visualization. So we can do that with ggplot with the function geom_jitter. And so everything else is pretty much the same. So our aesthetics, our x is our sex levels, y is our height, and so then our color and making it transparent, those are all the same. The one difference is this height equals 0. And so by default, ggplot or geom_jitter is going to add random noise to both the width and the height of the points. And we don't want it to add random noise to the height, right? Because that would actually change our data. So to make it not do that, we're going to set height equals to 0. And that's going to say don't add random noise to the height of the values, only add them to the width. And it's a little confusing here because the argument that we enter is height, so to tell it whether or not to add noise to the y-axis. In this case, our y value is actually called height as well. But this refers to any y variable, not to ours, that's called height specifically. So this is always going to be height, regardless of what your data are. So there's no relationship there between this height and our height, except for they both happen to be the y-axis in this case. Yeah, so then we get a plot like this, and you can see now we can see the real patterns of the data. There's less overlap between the points. It's still very clear, even though we've added random noise to the x-axis, it's still very clear which points represent males and which represent females. And so this is kind of a nice way to visualize raw data in this way. Kind of now what's trending is people doing both and plotting the box plot on top of the raw data. And so this is relatively easy to do in ggplot as well. So here I'm going to plot the jitter first. And so this is just the same as before. I've changed the color though, because if they're both blue, it'd be hard to pick things out. So I'm calling this brown, which actually looks red to me. And then plotting the box plot on top of that. And maybe this is a poor color choice here because it looks to me like the box plot has chicken pox or something like that. So maybe think harder about your color decisions when you're doing this. Anyway, so this looks kind of nice, right? We have the box plot summarizing the trends in the data, but we still see the raw data. And so this kind of covers a lot of bases. One issue that we see though is that the width of our jittering is wider than the width of the box plot. So if we're being really anal about it, we'll want to change that so that these are the same width. That's easy to do. So we can change how much they're jittered on the x-axis with the width argument. Remember, we set the height argument to 0 because we don't want to jitter it in the y-axis, but we can customize how much it's jittered on the x-axis with this width argument. So by default, the width is set to 0.4 or 40%. And so I'm just going to lower that a bit to 0.35, and that's the only difference between this plot and the other one. And you can see now all of our plots fall within the box plot, like in terms of the width. And so this looks a little bit nicer. So there's a lot of different plotting functions. We just have one more that we'll look at. And so this is using the ggridges package. And I actually like this quite a bit when we have categorical data. And it's actually going to be more informative the more levels that you have in a category. And you'll see this throughout the course. So here, the first two lines are the same. The function for drawing this, once we've loaded the ggridges package, is geom_density_ridges. And so our aesthetics, our x is going to be our height. So we're switching the axes now because now our categories are going to be the y-axis and height is going to be the x-axis. So x is height, y is going to be our sex levels. And we want to group the data based on sex. And then here we're just changing the color, making it transparent, and customizing the x-axis labels. And that looks like this. So you get a nice feel for the distribution of values. So we can see, different shapes of distributions of heights between males and females, which doesn't really come across that clearly in the other plots. If we want to get really fancy, we can change the color depending on what level of our categorical variable we're at. So here, all this is the same, except for now I've added this argument. So the fill color for each histogram is going to be based on the sex. And then I don't want to use ours or ggplot's default colors. We're going to manually change the fill colors. And so changing them to brown and Dodger Blue 4. And then I don't want to, by default, ggplot will add a legend anytime we group things and color them by a variable. It'll add a little legend here, but it would just, our y-axis pretty much contains all the information that we need, so we don't need a legend. And so we get a plot like this, which is a nice way to visualize it. Okay, so those are different ways to visualize data. Hopefully some of them are useful to you. Play around with them. We'll use them all throughout the rest of the course. But before we change videos, now we're going to do the frequentist approach. So we're going to analyze the data from a frequentist approach. So often when we have two groups, so in this case we have height data for two groups, if you want to compare them, usually you'd use a t-test for something like this. So we'll go through how to do a t-test in R. In order to do this, the data must be organized as two vectors, one for each sex. And so first we can just remember that we know the structure of the data, so we can use the head function to look at this. So we have height, weight, age, and sex. And then we can make one vector of the height of females is just going to be from the adults data frame. It's going to be all rows, so before the comma, all rows where the sex field is female. And then from those rows, we want the first column, right? The first column contains the height. So remember on our very first day of class, we went through a bunch of ways that you can split up data frames in R using different functions like this. So now you can get some practice and see just how useful they are. And then we need another vector for all the height of males. This is the same idea. So from the adults data frame, we want all rows, so before the comma, where the sex field is male. And from those rows, we want the first column. So that will give us the height of all the males. So this is how we can parse out the heights of females and males. So then we can do a t-test. So to do a t-test in R, the function is just t.test. and we're comparing the height females vector that we just created with the height males vectors that we just created. So if we do that, we'll get our statistics here. So our t-value, our degrees of freedom, our p-value. This is the lowest p-value that you can get in R. So surprise, surprise, there's a statistically significant difference in the height of adult males and females. We also have our estimates of the mean for each of those values. And we mentioned early on that a lot of the different tests that you've used are actually really just different forms of linear regression. So now we'll also go over how to analyze these data from a frequentist approach using regression. And it's very easy. So it's the same idea as what we did before. We're going to use the linear model function, so the LM function in R, and we're comparing the height data to the sex data. And so this is, we have kind of the syntax for this linear model function in R is you have the predicted variable and then this little tilde and then all of the predictor variables over here. And so here are predictor variables sex, and we're going to save this model and we're going to call it model. And then we can look at the results by typing summary model, and you get all of this information here. One interesting thing that R does by default when you have categorical data is instead of this being the intercept, it sets whatever value is 1 for that factor. It sets that as kind of the default, and then everything else is comparison to that one category. And so that's actually our intercept. So remember, we have 2 levels in our category, females and males, and females were assigned the value 1 and males were assigned the value 2. So this intercept here, it's actually the mean height for females. And again, R just does this by default. So this is the intercept for females. So this is the mean height for females. And so what this p-value is saying, the mean height for adult females is significantly different from 0. So it's good that we did that test, otherwise we wouldn't know. And then what this parameter is it's the difference in height between males and females. And so the average height for males is the estimate for females plus this coefficient. So plus is 10.9946. So our estimate for the mean height for males is 160.4921. And then this p-value is comparing this to our males to females. So this is saying there is a significant difference in height between males and females. So that's how we can do this. And you can see, I guess these are so low you can't compare them. But if this was higher, you'd see we get the same p-value from this linear model as we would from a t-test. So you actually never have to do a t-test. And to me, thinking about it from a linear model framework makes a lot more sense. Because when you think about things, again, the idea is to step away from memorizing a bunch of different tests and when to use them, and instead to have a principled approach to how you analyze your data. And so thinking about things in this way, I think will make you much more flexible in your statistics and be able to deal with more problems. Instead of memorizing a bunch of different test names, you can just build an appropriate model. Okay, so that's it for this. We'll stop this video here before I move on to a Bayesian approach.